that are distinct. It's just essentially illustrates the same. Okay, I now do want to go to semantics, and I want to do that by first recalling what semantics was in the propositional setting. What do I need to give meaning to a formula?
Regulations?
Yes.
Interpretation.
Well, we call them interpretations, indeed. If I have a propositional formula, I want to give it a meaning, I have to tell you what the propositions stand for. In particular, I have to tell you of each proposition whether it is true or false. And we called that an interpretation. An interpretation was a function that for each proposition tells you if it's true or false. We are now in a much more complicated setting, where we don't only have propositions, we also have these predicates. So we'll have to tell of all these predicates and also of the constants what they stand for. The semantics will have to tell you this, otherwise you still don't know what a formula means. So the semantics of a predicate formula consists still, we call it still an interpretation, but the interpretation is a much more complicated thing than it was before. What does the interpretation consist of? First of all, we need a domain. Every predicate formula talks about a domain. That's the domain from which the values are chosen that are used for the variables and constants. For instance, the domain of natural numbers. For instance, the domain of people in this lecture room. For instance, the domain of skaters on the skate rink. Just a set of individuals that you're going to talk about. That will be the domain. If you don't have that, then your predicate formula doesn't have meaning. Secondly, I have this set of predicates around, which for now I'm calling P1 through Pm, but for examples were sitting next to each other, being a mother, being larger than another number, we're talking about that one. All those are predicates. Once we've picked a domain, we can also say what the predicates stand for. Because now, the predicate really will be a set of values from the domain, or a set of pairs of values from the domain, or if my predicate had 3 parameters, it will be a set of triples of values from my domain. But all my predicates will actually correspond to subsets, to sets of values. Yeah, so that's what the second line says. Each R sub j, so my interpretation consists of that domain, then a set of, well, a set of sets of tuples. Each R sub I is a set of tuples. And it here says a set of alpha tuples, where alpha is the multiplicity of the predicates. So if I'm talking about predicates with 1 parameter, then alpha equals 1, and then my set will be a subset of d to the power of 1, which actually is just the domain itself. If I'm talking about binary predicates, then this alpha is 2, and then I'm talking about subsets of d to the power of 2, which means the Cartesian product of d with itself, which then therefore means that I'm talking about sets of pairs. We will very rarely see predicates with more than 3 parameters, but the whole story extends to predicates with arbitrary parameters. So if there are more than 3 parameters, then the interpretation will be a set of triples, or a set of quadruples, or however many values you need to cover all the parameters of the predicate. Then, the last thing we need is to give values to the constants. And that means just for every constant that I have in my vocabulary, I need a corresponding value. So the whole interpretation consists of the domain, a set of tuples for each of my predicates, and a single value for each of my constants. examples. I think you are direly in need of examples. Okay, let's take the formula over here. The formula says for all x, p a comma x. Let's think of sensible scenarios where this can be interpreted. So scenarios, I say, but in terms of what I just said, there are interpretations for this formula. Let's think of sensible interpretation for it. Who has a sensible interpretation for this formula? For all x, p a comma x. A is a constant.
For all natural numbers,
Yeah, well, that is a very good start.
yeah, there's a number that is small. There is a number a that is smaller than all the natural.
Yes. Well, actually, it doesn't say there is a number,
For all.
but A stands for the number. So you already, if you would say there is a number, well, it sounds like you're saying exists y such that for all x, but indeed, the number should be assigned to constant A. For instance, it could be 0. So if you pick as your domain the natural numbers, as the interpretation of P, the relation smaller than, as the interpretation of A, the number 0, then this is actually a true formula. It expresses a fact about the natural numbers. Now let's go to another domain. Who knows another domain where this is also true? Let's talk about strings. The domain of strings. In the domain of strings, can you give me a binary relation? Yes?
That the length is always longer.
Okay, so the length of a string, yes. So then the relation would say that one string is longer than the other. That's a perfectly good relation. Then is there, what would be a good value for A such that this is true? Sorry? Interesting string choice, but then at least the statement isn't true, because it's not the case that for all strings their length is larger than that of hello world. The empty string. For the empty string it is true, yes.
Yeah, but doesn't interpretation always have to be true?
No, absolutely not. No, I asked you for a setting where it makes sense, and it definitely makes sense also for A being hello world. But there are lots of settings where this makes sense, and also lots of settings where it's true. And there's another one on the sheet where the domain is actually the domain of booleans. The value for A is the value is false, and the relation P is the implication. This is a bit tricky because I'm now hiding the interpretation of booleans inside the predicates of my predicate logic, and of course the logic itself can also be understood as talking about booleans. So now that's booleans on two levels. This is just designed to confuse. Yeah, but it does say that for all booleans, false implies that boolean, and there are only two booleans around, so it's easy to see that's true. Yeah, false implies false, false implies true. So yeah, but confusing. Yes.
Do you have to have a constant for because in the formulas before we had x and y, for all x there exists y.
Okay. No, you don't have to have a constant. Actually, before you write your formulas, you essentially decide on a vocabulary. And the vocabulary, with the vocabulary, I mean the choice of constants and the choice of predicates. And you may choose not to have any constants. It depends on the kind of things you want to be able to say. Very often, I would say, if you talk about a concrete domain, then you have a lot of constants, because you have things in mind that you want to concretely talk about. But there are definitely also lots of cases where there are few or no constants. If you talk about natural numbers, we'll see this later in more detail, but if you talk about natural number, then people typically take one constant, namely the number 0. If you don't take a constant for the number 0, then it becomes kind of tricky to talk about 0. You could say it's the number for which there does not exist a number that is smaller, or something like this. But constants are I would say it's more like they're handy than they're absolutely indispensable.
What if we, because now we have a relationship between two constant and variable, what if I add more for a x and y, for instance, then how do I write down the implications for that?
Okay, I think that you might be asking two questions at the same time. So this is an example of a closed formula, right? Closed meaning that all the variables that occur have a binding quantifier outside. If you have a formula with a free variable, like y, without a quantifier for it, then of course, in order to give meaning to the formula, you still have to give a value for that y. That will be on the next slide. Okay, but for the main message here is this one. What do you need to give to give meaning to a formula? Yeah, and I'd like you to remember that an interpretation in the setting of predicate logic needs the components of the domain. We're talking only about a single domain here, which is to computer scientists a bit confusing because we're used to thinking in terms of types, and there are lots of types around. We have